Okay, welcome back to Chapter 18 on amines and amides. In the last lecture, we talked very generally about amines, and we dealt with the nomenclature and priority and all that good stuff. And so here we are ready to move further into Chapter 18, amines and amides. We're actually going to hold off on the amides a little longer. So in this lecture, we're going to focus on the properties of amines. So one of the key features of amines, at least the primary and secondary amines, is that they contain polar nitrogen-hydrogen bonds, which will allow those primary and secondary amines anyway to form hydrogen bonds with water. Nitrogen is not as electronegative as oxygen, right? Oxygen's about a 3.5 on the Pauling scale, and nitrogen's a 3.0, so it's decidedly less electronegative, and that results in weaker hydrogen bonds as compared to those found in alcohols. So still significant and still resulting in a general good water solubility for small carbon count amines, things like 4 carbons or less, we'll say, but not as significant hydrogen bonding either with themselves or with water as compared with the alcohols. So since we've already mentioned it, solubility in water, amines are soluble in water in general if they have 1 to 6 carbon atoms, although you do have to be careful about that because it depends on how those carbon atoms are distributed. So generally primary amines are most soluble while tertiary amines are least soluble because the nitrogen atom in the smaller amines forms hydrogen bonds with the polar OH group in water. Notice in the case of primary amines, you can have hydrogen bonding with the amine lone pair on that nitrogen as a hydrogen bond acceptor, or from those 2 NH bonds, they can be hydrogen bond donors to lone pairs on water molecules. For secondary amines, you can still have a little bit, right? You can still have the hydrogen bond acceptor on the lone pair, and you can have the one remaining NH bond can be a hydrogen bond donor to the lone pair of a water's oxygen. Finally, for tertiary amines, you have no NH bonds, right? So all you can do there is to accept the partially positive hydrogen from a water molecule into the nitrogen's lone pair as a hydrogen bond acceptor. So you do have much less hydrogen bond possibility and much less water solubility if we're dealing with a tertiary amine compared with a primary or secondary amine. So this is probably a good place to stop for a learning check. So in this learning check, you're asked to consider the following compounds, 1, 2, 3, and you're asked which compound has the highest boiling point, which compound or compounds is/are soluble in water. So go ahead and be careful to consider those compounds. Not all of them are amines, so take that into account. Stop the video here while you complete your work and start us back up when you're ready to check that work. Good luck. Okay, so there we have it. Which compound has the highest boiling point? Hopefully you picked the primary amine. I think we were so focused a few slides ago on the idea of primary amines being able to hydrogen bond with water. We didn't mention, of course, that they can also hydrogen bond with themselves. Primary amines can make the most hydrogen bonds with other primary amine molecules. Secondary amines can make 1 hydrogen bond donor, 1 hydrogen bond acceptor bond per molecule, and then tertiary amines, of course, can make no hydrogen bond pairs because they don't have any NH groups. They can hydrogen bond with water as a hydrogen bond acceptor, but they have no NH bond to be a donor. So primary amines have the highest boiling point, secondary amines have somewhat lower, and then tertiary amines would have the lowest boiling points of the amines. In this particular example, where we have plain old alkane for number 3, that would have a lower boiling point than any amine. For B, we're asked which compound is/are soluble in water. Well, both amines would be because they're small amines, 3 carbons total for the amines in number 1 and 2. So even though number 2 is a secondary amine, because it's a small secondary amine, it should still be pretty soluble in water. The alkane, of course, no water solubility, so to speak. If this went well, great. If not, hopefully my explanation there for A makes up for any glossing over of that feature earlier. And if you're still struggling with either Part A or Part B, please do reach out for some help. Another property of amines is that they tend to be basic, at least to some extent. In water, definitely. As long as we've got some water solubility, we'll have some base activity. So amines, just like ammonia, have that Bronsted-Lowry base property. They have the lone pair, right? Primary, secondary, tertiary amines. Doesn't matter as long as they can interact with that water on that lone pair on the nitrogen, you're going to have basic behavior. They're going to be weak bases in water. And we see that base dissociation, the lone pair of the nitrogen accepts the H+, the proton from a water molecule, making an ammonium ion and leaving behind a hydroxide ion. So here we see it with ammonia, works the same way with a primary, secondary, or tertiary amine. So now we looked at water behavior, the amines act as bases. We can also make salts of the amines, and that happens when we neutralize an amine by an acid. So this is very commonly done with medicines. You'll often see medications that are given as hydrochlorides because they have a nitrogen of an amine group somewhere in that structure, and in order to make it more water soluble, you convert it into the amine salt. The way we denote those is by replacing the amine part of the name with ammonium, and then follow it by the name of the negative ion. So for instance, we see a couple examples there on the slide. There's methylamine, which is neutralized by hydrochloric acid to form methylammonium chloride. In the case of dimethylamine, rather, again, an HCl, whether it's in water as hydrochloric acid or just the gas hydrogen chloride, either way it accepts that H+ into the nitrogen lone pair to make a coordinate covalent bond, and then it forms a salt with the chloride ion to form dimethylammonium chloride. So that's just something to look out for as we do change the name from amine to ammonium, and then we do have to name the counter ion when we make an amine salt. Some properties of those amine salts that we generate, they are ionic compounds, so we do expect them to be higher melting, higher boiling than the plain old amines. So they are typically solids at room temperature and pressure. They tend to be much more soluble in water and in body fluids, which is why they tend to be the form used for drugs. So many drugs have that amine functional group, and in order to make them better solubility in the body, we tend to almost always make them as hydrochlorides. That's almost always what you see, and there you see a couple examples, right? Ephedrine hydrochloride is the generic structure of Sudafed. Then we have the diphenylhydramine, HCl, the diphenhydramine hydrochloride. That's your classic Benadryl structure. So again, in the first case, we have something that is used typically as a nasal decongestant. For Benadryl, it's often for allergy relief there in that structure, but they're both examples of amine salts. If we go to the illegal end of drugs, cocaine's a common example that either exists as the amine salt or as the free base. So we have on the left cocaine hydrochloride. It's typically a much more pure form, so it's generally reserved for your celebrities, your businessmen and women, people with some money who choose to engage in illegal drug activity. They tend to be your high-end cocaine hydrochloride users, and these are the ones who will, roll the $100 bills and sniff the lines of coke because it's very body soluble, so it can get in through the nose or through other tissues that are going to be in contact with the powder and allow for water solubility. On the other hand, we see the free base form, which chemically speaking is a very good name for it because it is the free base. It's not the hydrochloride, so it's the amine base. In this case, we see it as a tertiary amine. There's that nitrogen up toward the top, so it's a tertiary amine. It does have a lone pair. It is a weak base, and so it's sort of impressive that it's known as free base, but it's also known as crack cocaine. It's generally much less pure. generally smoked with a crack pipe because it's not going to be as soluble in the body, and therefore you're not going to be able to snort this through $100 bills or even $1 bills, since we tend to be dealing with less affluent users. The cocaine freebase tends to be smoked, and unfortunately oftentimes there's incidents where there's a flare from the crack pipe and people get burned. It's really unfortunate. Any of the drug abuse certainly is unfortunate, but freebasing in particular is fraught with peril. So just letting you know about these forms of cocaine. Hopefully you're never in a position to try either. Okay, so let's go ahead and end the lecture as we often do with a learning check. So this time you're asked to write the equation for ethylamine when it reacts with each of the following. So first, when it acts as a weak base with water, and then secondly in a neutralization reaction with hydrogen chloride. Please stop the video here while you write those reaction equations and start us back up when you're ready to check your work. Good luck. Okay, so hopefully you came up with something like what you see on the screen here. It doesn't matter which order. You could have the water molecule first and the ethylamine or ethanamine if you want to use the IUPAC name. It doesn't matter which comes first, but those should be your two species on the left. Notice the double arrows. It is an equilibrium process. It's a weak base, so most of it stays as the ethanamine, but some of it does convert into the protonated form, ethylammonium hydroxide in this case. The water is split apart into the H plus that's accepted into the lone pair of the nitrogen, and then the OH minus left behind as the counter ion. For B, notice it's a single arrow, and that ethanamine can be the first or second reactant. Doesn't matter the order there, but it should be ethanamine and hydrogen chloride in either order. And then a single arrow because it is a completion type reaction. Because the HCl is a strong acid, it does fully protonate that nitrogen to form the ethylammonium and the chloride counterion. So please reach out to me if you had trouble with either of those. Otherwise, I will see you in the next lecture of Chapter 18.